Okay, first, thank you for joining my presentation. So today my presentation it's about like AutoML time series forecasting for infrastructure resources. So a quick introduction about myself. I'm Heping Liu. Have been in the Bay Area more than 10 years. Like I have been working for the machine learning since I got my PhD degree. And recent 5 years I have been working in Workday. So just a quick introduction about Workday. So Workday is international cloud-based on-demand human capital management and also financial management and student information system. So it was founded in 2005. So it's Nasdaq 100 and Fortune 500 recently joined the Fortune 500. So it's president-based, and the revenue into 2024 it's about like 7.26 billion. The number of employees is a little more than 18,000. So let's take a look at what I'm going to present. So today here I'm going to present first why time series forecasting for infrastructure resources, and then talk about the architecture of recipe managed AutoML time series forecasting, and then talk two major components within this architecture. So one is the big data ETL pipeline engine. Another one is recipe managed AutoML time series forecast engine. So once this is done, I'm going to present two application cases, and then conclude the presentation. Have a few minutes for Q&A. So first, why time series forecasting for infrastructure resources? Like, as we all know, like here for infrastructure resources include storage and computational resources such as physical server, right, and the MySQL server, JVM memory, disk size, and CPU, and so on. So we know like the operations monitoring and the demand planning require to project the future demand so that these resources can be appropriately provisioned and optimized. So this talk it's going to introduce a recipe managed time series forecasting which uses Spark to automate and linearly scale up for millions of time series and run them in parallel. So the forecasting framework here uses not only to adjust the daily dynamic provision of resources to satisfy the fluctuation transaction, but also the long-term planning to achieve and maintain the supply equilibrium. So the forecasting framework here, although it's talking about that, like, for infrastructure resources, but in fact, this can be extended to different time series forecasting applications. Like, it's a very generalized one. So the forecast framework can handle a few scenarios. Like typically for the application, it can be, for example, here we can see short-term and the long-term. So for the short-term, they can add different levels, like specifically, like, for example, tenant level, service level, and for different metrics. And they can also be aggregated at the like server level, data center level. Like in that case, for the monitoring, and another thing is they can for the optimization. So for the long-term, I think it's a similar situation. They can be aggregated as well. But for the long-term, here it's more about like demand planning. The reason is like the demand planning is usually for the long-term in that case. So here for this one, like once we have forecasting results, there are many applications on top of that, then we can have optimization, right? And for the optimization, can have different types of optimization, such as fixed validation and also like delayed patch and so on. So let's take a look at like specifically because this is some background. Like with this background, we can understand the rest of things for the resource forecasting. Like so here, let's say we have different tenants, right? Tenant 1, tenant node N, and they're working in this data center. And for this tenant, there are multiple services. And then for this service, we can provision this different type of resources. So this is the situation. So in this case, here is a short-term situation. In that case, it's more about computation and storage resources to be provisioned to support the transaction. So in order to provision the approved resources, the demand of resources need to be forecasted in that case, so that we know how much to provision, and then we can pack them together to minimize the number of servers in that case. And for the long term, it's more about demand planning. So in that case, long-term planning is a little different. So it's more about realizing the equilibrium of supply and the demand at its aggregated level, such as the data center, for example. So Workday spends billions of dollars annually for the infrastructure. So the general purpose process for the demand planning is to forecast the demand and optimize the supply, and then analyze the stock to ensure that the supply meets the demand. So this process continues to be iterated so that the company, in that case, can be has the adequate capacity to meet the needs in the daily work. And the service level aggregation in that case can be achieved while avoiding over provisioning and also unnecessary cost in that case. So here is the architecture for this recipe managed AutoML time series forecasting. So here we can see it is starts from here external source two major components. One is this component, another is this component. So these two components, first one is more about the data connection. So data connection are used to connect the different types of raw data and process them and then store them in the specified data storage in this framework. So data connection, this pipeline, implementation of one big data ETL pipeline framework, which is developed by us. I will talk about that later, in a detailed way. So the connected data can be any metrics of resources, then obtained through observability tools, such as instance memory here and user disk size, data disk size for the MySQL, for example. So the key component is about this part. So here the key component is that the recipe matched AutoML time series forecasting engine. The whole forecasting work, they divide to be independent modularized task. So a forecasting recipe is formulated by organizing these tasks according to the needs of developers. The chart here shows the basic modules frequently used, but not just these modules. There are more modules, and this is just some examples, and they're quite often used. So in this chart, it's not needed to, if for example it's not needed to MySQL, we can exclude it so that it's quite flexible in that case. There's one UI on top of that. So once the forecasting is output here, then we have UI to show it in that case. So let's take a look at this part. So the reason is why we need this big data ETL framework to connect the data. The situation is, initially this part was not particularly emphasized when we're building our forecasting engine. So later on, the reality told us this is quite important. The philosophy behind this is that data is the key for the forecasting engine. So getting and updating the data and should be run smoothly in that case. So here we can see the reason is, for example, for data connection, they have been done by different engineers, and the code, for different teams when they run it, they may sit in the different repository even. And some teams are using Python, some teams using Java, and some teams using shell script in that case. So which makes the management and the maintenance of the code very difficult. So that's why we design this one. And another thing is for different teams, when they do that, there's a significant number of codes in the different data connection. It's the same, or similar. So it becomes unnecessary to repeat this type of work. So we designed and developed this lightweight big data ETL framework and used to connect and process data for the different sources. So in that case, the data connections sit on top of that like big data ETL and become an important component for the forecasting engine. So here, internally, this is a Spark-based big data ETL framework. And also, it can manage multiple heterogeneous data connection in that case. The big data ETL, like here, is divided to be different modularized tasks. We can see that later. And the type safe managed configuration management. So it's very convenient to configure the files, like the properties. So here's a pretty high level the architecture about this big data ETL. So we can see we can connect data from different sources. This is reading data, right? And then reading data here is managed by this flow chain. Here, they can read the data from different sources. We just need to identify whether it's HDFS, and then it goes to here to that. If it is S3 or some other like MySQL, we have developed this one, and then process the data tasks. They have multiple different types of process data tasks according to in the reality we developed them. And then here they could have multiple, and then write data different locations based on what the customer need in that case. So it's pretty straightforward, but it's very useful. Next, let's take a look at this part. Let's manage the time series forecasting engine. So here the whole forecasting engine it's divided into different tasks as we mentioned. And then let's first one we can see from here it's a driver, and this driver basically is managing the whole process. And then the next one is the loading data from different sources based on the application. You can define yours, but this is a framework. You can use it. And in that case, for the recipe, you just plug your your loading task in that case. And here, once let's and then we have a task for time series formatting, and then run the forecasting output processing, and then to different locations, this different task. Let's internally take a look at this particular time series forecasting this task. So once data is loaded and pre-processed in the Spark, right, and then formatting task will start. In that case, we generate time series, in terms of giving mode ID. So for example, here we can see once they know where the data is sit, let's say sitting in this table, and then we say mode ID is it's like a combination of data center, environment, and tenant name, and also service type. And the metrics, what I want to forecast, for example, it could be memory or could be disk size. Then in that case, for formatting task, they basically extract the data to formulate the mode ID. And then here we can see this is for the memory, for this tenant memory to do the forecasting for it. And so that they extract data. And here we can also see this is for the disk, then extract it, like this process formatting task will take data out and format data to be a specific time series. So this is base like a time series in that case. And once this is done, like in the reality, we can have different aggregation. For example, I want to do the memory forecasting at the service level. Then here we do the aggregation for this tenant. Then we generate this one in the formatting stage, do the aggregation. So this using Spark, this is very straightforward. But if you repeat this one, it's going to take time. But in this time, you can just very quickly to format that to generate the different time series. So this is here we can see for the service we just need to add one more step to formulate that. And for the service level, memory forecasting or disk side forecasting very quickly to generate that. And then if we want to say, for example, I want to at the data center level, then here this is just need to aggregate this one to generate data center level. For example, this is data center environment type, and for memory to do the forecasting. This is for the disk side forecasting. So this is based on the base time series to generate aggregate the time series in that case. So here, there's another thing is, we did this, we can do the aggregation at the geographic level, for example, data center, right, or service level, different type of service, and we can also do the aggregation at the frequency. For example, this is based on time. If we want to do the forecasting for this service. At the weekly level to do the forecasting, then this we just need to format the data for the time, and then do the aggregation for the time, to generate the time series. So this we can see data center level, service level, or time level, or any combination between them. So that once the time series is forecasted, so the next step is we need to forecasting, right? Using AutoML to forecasting it. So let's see how this part is working. So because we have so many time series, could be thousands or 100,000 or million level time series, then in that case here one important thing is data and the model scalability. So how to make sure that our data is scalable, that's a very important thing. So here we using Spark try to distribute based on the model ID, distribute the data to different workers. And then in that case, our forecasting engine is Spark-based distributed forecasting engine in that case. And within this engine, there are Spark driver we can see, and also forecasting context, which manages the distribution of data models and the models. So the data is partitioned and distributed. So then the whole system we can see from here, we can quickly scale up in that case. So if we have more time series, if you have 100,000, then you can use this amount of for the Spark cluster can be this configuration. If you have million time series, then you can have bigger, cluster in that case. So this is linearly scaled up, so we don't need to worry too much about the size of time series, the number of time series in that case. Don't need to worry too much. So here now let's jump into this executor inside to see how that is exactly working. So here, this is how that is working inside this executor. So within one executor, the worker here we can see it's sequential down as described by this flow chart. So high level, it has maybe have three steps here and here and here. So this is part from here to here is more about processing data. And this part is more about building model and forecasting, and here is post-processing and export. So we can see in the first step, when data enter that worker, so data, in the reality could be, it may have exception, we need to handle that. It may timestamp may need to be fixed for some reason, and may have duplicated data. We need to run the dedupe in that executor. So this is some more related to data processing. And once this is done, the second step is more focused on statistical analysis because the data could be outliers, and we need to use some statistical way to exclude outliers. And the data might be missing because we are once data is sequentially, some days of data might be missing. Then we need to use a different way to run the interpolation to fit to build our the time series. And the second part here is and then goes to the model side. Here for the model side we have time series is a constant thing. We will see seasonal or chain decomposition. This is the one thing which need to be handled. And then once this is done, we have pretty good time series. And then here we fit this time series to different types of models. We can have different types of models for sure to evaluate which model is the best one, and select that model using AutoML to select that one, and then use that next step to run the forecasting for that. And here, there's one thing is because sometimes it's often when we run the forecasting, in the academia we may say, okay, we just run one step, a couple of steps ahead of forecasting. But in the reality, when we do the work, it's constantly get asked, like, I want to forecasting for future 60 days or maybe 180 days, or 5 years forecasting, like a monthly time series. So in that case, model is just model. They may, in that case, if it go up or go down, if it go down, could it become negative, right? If time horizon is pretty long. So, but it doesn't fit the business situation in that case. So we need to have some process to process the post process to make sure output fit the business situation. So once this part is done, we output data. So this is how that is happening in that in that executor. So here we mentioned models, right? So how that model is used. So how AutoML is working for that particular model. It could be different types of model. And here I'm using all the ARIMA time series models as an example to explain how AutoML is working particularly. So we can see, for time series ARIMA, here this is ARIMA PDQ. So P is autoregressive, the order for the autoregressive, and the moving average, and D is more about difference, try to use difference to remove the seasonality, make sure or union root, make sure the data is stationary. And here for that one, we are going to for different. It's going to have a set of PDQ, and for that set of PDQ, for each each PDQ combination, we are going to estimate phi I and theta j, so that we generate one time series, and then we use different statistical ways to evaluate whether this model is sufficiently built. So, for example, using a BQ test or Dublin-Watson test, and to test whether this model is built successfully. So another thing is, could be have exogenous variables to be added to the forecasting model for sure, to improve the accuracy. This is ARIMA one. In fact, it's not just for this model. It may not just ARIMA. It could be any model based on what you need. You can select different types of models, but the idea here is similar. You run the model, evaluate different combination to select the best one based on the evaluation. These are different types of models you can use. So I just talked about forecasting engine. So this engine can be further generalized to be a service. So here we call it the forecasting as a service. The reason behind this is that we see that there are many teams, they want to do the forecasting for themselves for different types of reasons. But they do not have good, either they do not have good forecasting skill set, to scale up so many time series forecasting, or they do not have big data processing skill set, or maybe due to some reason, for example, data security reasons, they cannot expose the data to the members outside the teams. So in that case, we try to make sure this to be generalized and can be deployed easily. They can use it even without too much knowledge, big data knowledge or forecasting skill set. So here, for this, in that case, here we can see it's basically have three things. One thing is recipe-based, forecasting engine, as we just described, with distributed computation capability. Another one is big data ETL. This one is connect and process data from diversified data sources. And once connect it, store it, we run the forecasting automatically and generate output, and they have UI to show them, and they also have API that can integrate with other services in that case. So this makes it highly automated in that case. Here is some things to explain how that is exactly working. For example, in the configuration file, they can specify, where the data located, this database, this schema, and this table, and tell the service to say, okay, I want the forecasting for this table, for this metrics, and here is my model ID, the combination based on this. And once that information is given, then this configuration is configured. And so this configuration will be used by big data ETL to connect and process data. And then once that is connected and processed, then forecasting engine kick in, and then they take the data to build the model, and they feed the model and run the forecasting. So once the forecasting out it's forecasted, they store data back to the database, which the location can be specified in this configuration file. So once the data is exported, they can there's a UI which can connect it to show that like. So here we can see like and it can also be integrated with other services using API. So here we can see basically it's this part and this part. This is three major things like. So here is the how that like configuration file looks like. So here for this time series like configuration file, basically it's a recipe we call it. So they can have multiple modules. And for this module, like they define for each module, for one modules, here we can say, okay, I'm forecasting for this table, for these two columns, these two properties. We just, if there are, for the table, there are multiple properties, we just need to add one here. Like it's quite convenient, and users can quickly do that. Like, and they can specify some other parameters in that case. So using this one and this configuration file will drive the whole process to get the work done. So to summarize that, like, so for this one, it's basically user give a set of metadata information, including the database host name, schema name, table name, and what they want to predict, like, and the metrics name and the output location. And with those information, and generates time series in based on different based on the specified in the configuration file, and then build the model, connect data, build the model, process data, export data, and then we have visualized the result API ready to do the integration with any other applications. So 3 steps here we can see. So like next, I'm going to talk about quickly talk about 2 applications. Like so, one thing as we mentioned previously, like we have short-term application and long-term application. So for the short-term application, a typical situation is monitoring operation. Another thing is optimize the situation, like optimize the system. Like so. We have built like, for example, for this situation, like once we have different tenants, and in multi-tenant environment, they will sit in one server, and here we forecast their size. The next thing is we want to ask, like, can we host these 6 tenants by using less servers in the future 6 weeks? Because we already forecast the future 6 the values for the future 6 weeks, and then we can based on the to say, okay, for the multi-tenant environment, whether I can reallocate this tenants to make sure I'm using less server in that case. So this is one typical application, as I mentioned before. It's more about reduced hardware in that case. So here we can see, this is the application. Another thing is for this one, basically, we can see like once we build like 0-1 integer programming, then we are going to find actually we can use less servers to host these 6 tenants, and we are going to empty one, then which means we're going to use less servers in that situation. Like, and this is how like that optimization model looks like. I'm not going to cover too much about this one, like, but just want to mention like this optimization model. The data is based on the forecasting one here. Because we are going to process that for the future 6 weeks. And there are different types of application, as I just mentioned, for those 2 charts, like reduce hardware, right? And if for the future we forecast it may business maybe violation may happen, then we need to fix a big violation. And if we forecast in the future, like to say delay the patch, we wanted to skip some patch cycle or patch window, then we can provide enough resources based on the forecasting output, and also maximize the lifespan like for resources. So here we can see like 100,000 forecast model automatically built, like based on that the pipeline. And typically for the short term, we forecast in future 2 to 6 weeks. So here, I think just give some numbers that we can quickly understand how that looks like. So here, assume that we have 5 data centers. And each data center, we have 4 environments, such as info, preview, prod, sandbox, right? And for that data center, we have 5,000 tenants per data center per environment. And if there are 3 metrics which need to be forecasted, and then in that case, this is how many time series which going to be there. It's going to be there. Like it's 300,000 time series will be processed and forecasted in that case. So data is, it's quite it could quite like highly fluctuated. For example, it can be the chain can be suddenly changed. For example, for this one, like at some time point, but you need to, the AutoML need to be able to catch the new chain to do the forecasting, and they can be sparse sometimes, and also there's some duplicate data, like it's quite like fluctuates in that case. But based on this, the typical situation here is our accuracy is quite doing well. Typically is about 95%. Like. So the second one, in the second long-term like resource demand planning, like so here it's more about at the aggregated level, as I mentioned before, like for example, thousands of monthly time series models can be built, because I wanted to say for the future, like how many resources I need to purchase. This is more like at the aggregated level. So in that case, here, for example, if I want to do the forecasting for future like 3 to 5 years, for example, then in that case I have monthly forecasting, and data is aggregated at the monthly level, and we forecast them for the future 3 to 5 years. So this type of forecasting is very helpful for determining procurement, because you need to procure purchase the certain amount of resources. You don't want to purchase too much. It's going to cost too much money, and the server is going to sit in the inventory. It's going to high inventory, like. But you also need to supply enough to make sure that satisfy the business, like make sure it's wrong. You won't have problem. And also at the quarter level and the annual level, there's a budget like for the demand planning. So this is about the long-term planning. But typically for the long-term planning, in that case, long-term forecasting here, data aggregated, the time series, number of time series is much less, and the data point is much smaller in that case. So here, okay, that covers 2 applications. So here are some conclusions. Like, so this talk basically, here we can see we present one framework for AutoML time series forecasting powered by Spark, and focus on time series metrics of infrastructure resources that can support ARIMA or other time series models. So I think here a key innovation is that the use of Spark-based and the big data distributed computation to automate and scale the fitting and the forecasting operations for millions of time series. And here we did present 2 applications. Like I think for these 2 applications, they're automated build around daily, and it's they support short-term operation and also long-term resource planning. Like this is a high-level innovative solution. It's efficient, easy to implement, and it's not just for infrastructure resources. It actually can be extended for different application areas. It's quite flexible. Okay, that covers all of them.